Thank you very much for being here this evening, joining us at the 10th International Conference on Mars. My name is Michael Mishna. I am the lead convener of this conference, and it's my pleasure to welcome all of you here to learn a bit more about Mars and to share in the excitement and enthusiasm we have for studying the red planet. I would like to take this opportunity now to introduce to you our moderator for this evening's discussion, Dr. Bethany Ehlmann.
All right, good evening, everyone, and welcome here to Caltech. As Michael mentioned, this is in conjunction with the 10th International Conference on Mars. The first one was in 1973. It was as Mariner data. We're just coming back from a flyby of the red planet. And so here we are 51 years later, and a plethora of missions later. So it's an opportunity to step back, reflect, and celebrate. So as part of that, the Keck Institute for Space Studies, of which I am director, working with JPL and our colleagues who are convening the Mars 10 conference, have put together the displays outside as well as this panel to really celebrate what we're doing. And by doing it, we decided to give you 6 stories from current Mars explorers where they were asked 3 questions. How did you become a Mars explorer? What are the most important discoveries on the red planet to you? And then what do you believe is next, or what do you want to see happen in Mars exploration? So the way that this is going to work is that each of our panelists is going to come up and give a short talk. This is going to last about an hour or so. Everyone gets 7 minutes. Everyone gets 7 minutes. And then we are going to go to an audience Q&A. So think about those questions. And there are microphones in the front here for you to step up and ask that question. So without further ado, we're going to go to the stories of the journeys at Mars. And we'll kick it off with Dr. Phil Christensen. Whoops, and if we can, go to the deck, thank you. So Dr. Christensen is a professor of planetary geology at Arizona State University, and he has been the principal investigator of multiple instruments that explore Mars, as well as elsewhere in the solar system. So with no further ado, Phil, the floor is yours.
Thanks. Well, it's a real pleasure to be here tonight, speaking to this group. I am going to try to tell a bit of a story as asked. I became a Mars scientist. I was working as an undergrad at UCLA. I took a class that had Bruce Joukowsky, Dave Page, and myself in it from Hugh Kiefer. So it was an interesting start. But I was actually, my first job was cutting up Mariner 9 pictures that Hugh Kiefer had received. And so I got my first taste of actually looking at Mars up close. One of the things I would say that over the course of my career that's been the most amazing is when I started in college, our data from Mars was grainy Mariner 6 and 7 images, and we were just starting to get Mariner 9 data. And if you've looked at Mariner 9 data, it's quite a long ways from CTX and HiRISE. But what was remarkable is back then, Mars was a little red dot in the night sky, and that's pretty much what we knew about that planet. And so throughout my career, it's gone from a little red dot to a world that geologists study, that we know almost as well as our backyard, that we have images and data from. And so to have seen that progression has been truly phenomenal. One of the real highlights of my life, I got to be at JPL the night Viking 1 landed. And in those days, grad students, we sat on the floor in the corner, told you can watch but don't speak. It was a different era back then. But I sat and listened to Carl Sagan and Ray Bradbury and Mike Carr and people speculate about what we were going to see when Viking landed in just a few hours on the surface of Mars. And so that ability to go from we have 200 meter per pixel images to we're going to land on this surface was truly phenomenal. Sagan, I remember, was convinced that we would see things moving. Most people thought there would at least be sponge-like or fungus-like things on the rocks. And so again, it was just a really fun time. You could speculate about Mars because we had virtually no information. We sat and watched this image, and so imagine, line by line, this image coming down. In today's world, this seems, ho-hum, but at the time, we had just landed on the surface of another planet, and it was truly phenomenal. And we were astounded by the data that we have. Imagine, we couldn't move. We sat and looked from this same perspective for days, weeks, and months. But again, it was just phenomenal to be able to say, we are on the surface of Mars. We're actually looking at details of that little red dot in the night sky. The other thing that's been truly amazing is to just watch the progression of the data that we have. This is a figure from the first paper I wrote back in the 70s. So you're looking at hand contours of nighttime temperatures of Mars. Again, a spectacular achievement. But today, we have, if you look at that little red dot where I had 3 or 4 hand contours, this is the quality of the type of data that we have today. So just that progression from knowing virtually nothing to the amount of information we have today. One of the things I tell my students, the first paper I wrote had 7 references. And it wasn't because I'm a jerk and I don't bother to give any credit to my colleagues. Well, that I may be, but that's a different story. But that's all we had. That's all there was to reference, okay? And I actually sort of pity the students today with, the amount of information that they have to digest and know and understand. And so just this incredible explosion of information about that little red dot in the night sky. In terms of the greatest discoveries, I think for me, it's the diversity of Mars. One of the things that really bugs me is reading, oh my God, ha ha ha, NASA's discovered water on Mars again. But to me, that's every one of those discoveries is exciting because each one of those types of minerals, types of deposits, that's a different environment. Mars is a diverse place. It has an incredible array of minerals and environments. And yes, we've discovered a lot of different types of water on Mars, places where water occurs. And so to me, that's been one of the greatest discoveries, is just how incredibly interesting Mars is to someone like myself who's a geologist. This is a world that believe it or not, we're just beginning to understand. And so for the future, I just hope we continue. I hope we do Mars sample return. I hope we have another generation of Mars exploration. And I look forward to coming back every now and then and listening to what we're learning. So thank you.
Okay. Our next speaker is Dr. Abigail Fraeman, who is a research scientist at JPL and the deputy project scientist of the Curiosity rover. So take it away, Dr. Fraeman.
Great. Thank you. Well, I guess like Phil just showed, I will show what inspired me to study Mars, which was another image of the Martian surface taken about 40 years after that first Viking picture. When this image came down, I was a 16-year-old high school junior, I believe it was. And this is the Opportunity rover. This was one of the first images that Opportunity sent back, a color panorama of her landing site. And if you remember what Phil showed from the Viking landing site, I think one of the first things you'll notice is just how different this looks. This was for me, the first hint of the diversity of Mars and the incredible things that waited for us to find with our surface rovers. The great thing about Opportunity was once we landed, we actually had the ability to drive off the lander and go check out those white rocks in the background. Those are what geologists call bedrock, they're geologic truth. And like Phil, I also had an amazing opportunity when this image came down to actually be at JPL. When that happened, I was doing an outreach program through a group called the Planetary Society, and I was in the room, and so there's me with my mind just being blown, thinking about how amazing it was that we were some of the first humans ever to see this, and then looking around the room and saying, wait a minute, these people all get paid to do this? And they know what this all means and why it's important? I want to do that. So that really kicked off my course of exploration. And here is a traverse of my career shown on the traverse that Opportunity took. This mission, which was supposed to last for 90 sols, which is 90 Martian days, and go about 600 meters, ended up going for 14 years and going over 37 kilometers. When it landed, I was hoping that if I was really lucky, maybe one day I would get to work on a mission like Opportunity. And then amazingly, I got to work on this very mission. So in the time that Opportunity landed, I went off to college. I studied physics and geology. I started graduate school where I studied planetary science with Ray Arvidson, who was the deputy PI of the mission. And he got me involved in the rover operations. Graduated, came out here, did a postdoc with Bethany, and then got hired at JPL and heard they were looking for someone to help out with that mission as the deputy project scientist. So of course, really wanted to do it and was with that mission until it ended. So it was a really special, inspiring thing for me and so cool to get to be a part of it. But in terms of Mars discoveries, I'll talk about my personal discovery, which was one I was involved in, and that's with Opportunity's follow-on rover, Curiosity, which is what I work on now. This is a picture of orbital data that has been put together by an image processor who does beautiful art. And if you look really closely, there's a simulation of Curiosity, and where Curiosity will explore as it climbs this giant mountain. Named Mount Sharp. As a graduate student, I was looking at orbital data like this over the area, and I discovered there was a mineral that was associated with this raised ridge called hematite. Hematite usually forms in water, and so I wrote a whole chapter of my thesis about the hematite, what specific conditions it may have formed under, why is this a ridge in the first place. And then I was so lucky that 4 years later, I got to be part of the Curiosity rover team when we actually got here. I got to help lead the team think about where do we want to drive, what measurements do we want to make to figure this all out and actually test my thesis chapter, which is a very rare thing in planetary science. So here's the actual image of what the ridge looked like, which I can't tell you, after staring at something for many, many years from orbit, actually getting to see it with your own eyes is so exciting. And what we found after exploring the area was it was actually a story of groundwater that had come up and cemented the rocks. They helped crystallize the hematite here, and they're the reason that it's standing up as a ridge. And that was something we really could only learn by being on the surface. And I think that links to the broader discovery that I'm really excited about Mars, and it relates to what Phil just said, is this diversity of water on Mars, and in particular, something we've been finding recently is that water underground at Mars was present, and it lasted a really, really long time. And we're finding evidence for this groundwater with almost all of our land missions on the surface. And so understanding what this means, understanding what it means for the periods of habitability of Mars, I think is a great avenue for future exploration. But on the day-to-day, what I'm really excited about in the future of Mars exploration is to continuing to operate these wonderful rovers that we have on the surface. Both the Curiosity and the Perseverance rover are still exploring the surface of Mars. This is the drive direction image that Curiosity sent down last week when I was putting these slides together, but this is where we get to drive our rover. We get to explore these rocks and see what's here. And, contrast this with the Opportunity picture and the Viking picture. Mars is this wonderful, diverse planet, and it is so much fun to explore. But in the biggest picture, one of the things that I'm also excited about when we continue exploring Mars, let's send more rovers, let's send more missions to the surface, but Let me play this video. Another amazing way that I would love to explore Mars in the future is by air. Many of you may have heard of the success of the Ingenuity helicopter. I know there was a model outside. And imagine if we could take instruments that we usually put on rovers and we put them on helicopters, and then we send them places rover can't go, like Valles Marineris, the biggest canyon in the solar system. Think of all the incredible things we would see and the incredible things we would learn about Mars. I'm really excited about a mission like that. Thank you.
Our next speaker is Dr. François Forget, who is a senior research scientist at the Centre National de Recherche Scientifique in France, the French equivalent of the National Science Foundation. He studies meteorology and climate science on Mars, as well as other planets in this solar system and beyond. Dr. Forget.
Thank you very much. It's really a great honor to be here in Caltech. As you can tell from my accent, I am French. And in France, when you you like science, math, and physics, you tend to become an engineer. Or the way the study or the university is done, you become an engineer. So I became an engineer. And a naive and clueless engineer. And the reason I'm saying that, when I say naive, it's because at the time I didn't want to be really an engineer. I wanted to be an explorer. I wanted to be an adventurer. So I did a lot of scuba diving. I did all the degree you can imagine, and I actually specialized in ocean engineering. I went to the offshore industry, and I worked on submarine pipeline. And at the same time, I was fond of mountaineering and polar exploration, and I spend lots of time camping on the ice, and I still go to the Arctic and Antarctica. But something happened, change of life. I was also clueless because the way it was, I didn't know about science. I didn't know that science could be interesting to become a scientific researcher, and it took me some time to realize that it was interesting. So what happened? Change of life. I was hired by the French Space Agency, CNES, to work on a Russian project. And logically, to work on a Russian project, I was sent to NASA Ames Research Center for 1 year and a half. And there, it was a project of a balloon. It was very serious. It was a lot of money was put in that on the Mars, actually 98 project it was. And there, I met scientists like Jim Pollack, Chris McKay, and Bob Haberley. And there I realized that's what I want to do. And then I realized that science is exploration, science is adventure. And of course, solar system exploration is like that, but any science is like that. So in fact, I think I would have been happy in any kind of science. Nevertheless, then I went back to France and started a PhD to become a scientist after 1 year and a half. Before going further, I want to mention that exploring Mars is not easy, and I will continue by giving my personal experience. So I told you I started at NASA Ames. I was working in a team very much involved in a project named Mars Observer. On this Mars Observer, CNES, we had a relay named the Mars Balloon Relay to relay the balloon I was working on. And what happened is that when the observer approached Mars in August 1993, well, it exploded. We lost contact. Then I told you, I went back to France. I was in the PFS, a spectrometer team, on Mars 96. It was a Russia European project, and to be short, it's now at the bottom of the Pacific Ocean. Then I became professional. I was in the team of an instrument named PEMIR actually it was at the time already a Mars Climate Sonder, I think, if I'm lost, on the Mars Climate Orbiter, 1999. I was with what we call a COI. So I was there at JPL in September 1999, And well, you may remember, during the orbit insertion, the orbiter flew at 40 kilometers in the atmosphere, burned instead of being above. I think it was due to a misunderstanding between the units Newton used by NASA and pounds used by Lockheed Martin at the time. Then I was a little bit involved in Mars Polar Lander, but not really officially. Then I was one of the chief scientists on the Mars Express project, including a British lander named Beagle 2. And Beagle 2 tried to land on the night, in the night of Christmas night in 2003, and it didn't work. And I won't reply to that, but the first committee of, investigation team concluded that it was my fault. The second team concluded it was not my fault. Then there were a project with our institution was very much on Phobos Grint in 2011. It's also at the bottom of the Pacific Ocean. And finally, Schiaparelli lander. This was really, I was co-PI of several things in 2016. And it worked very well during the entry. But when it was at 1,200 meters, it decided that it was too low and stopped. It crashed. So the conclusion, it's not easy. Sometimes people say, well, in French we say, am I a black cat? But no, it's not, space exploration is hard. So before concluding, I have many slides to show. And what I want to mention is the fact that the first mission really that was really a success, I was very much involved in that as an interdisciplinary scientist. It was Mars Express, the first planetary mission we had in Europe at the European Space Agency, launched in Baikonur. That was quite an adventure. We used the Soyuz Fregat rocket. And the small spacecraft, Mars Express, has been, I think, very successful, very cheap. Believe it or not, for those my colleagues here, the industrial contract with the company that made the spacecraft was $80 million. For the entire spacecraft, so we don't do that anymore. But it was, and many good instruments, I think very successful. You had, of course, the nice camera, but spectrometer, we could get the first near-infrared mapping of the mineralogy, and we could, my colleagues could detect the first clays and salts, and we could monitor many things. I'm an atmospheric scientist, and we could monitor many kind of things. For instance, we could see CO2 ice clouds. My thesis was about CO2 ice clouds, but we had never seen them. They were like in the polar night, or we didn't know, and suddenly, with my infrared eyes, we could see them, and that was exciting. We could get the first measurements, remote sensing measurements in the upper atmosphere, which was an ionosphere, and I could go on and on. A lot of nice measurements. So for us, it was nice to be among our colleagues with NASA that have already done a lot to contribute. It was really fun. One of the things that we could do is discover and contribute with to find the existence of glaciers where you don't have ice now on Mars. Ice is not stable on Mars except at the pole, but we could find rock glaciers in many locations, including near the tropics on the side of the volcanoes. And that's one exciting finding we had, is that one day we had a workshop many years ago, and Jim Head, I don't know if he's here, reported that these yellow areas that were mysterious were related to glacier remnants. They were glacier, and at the same time, following talks, I show, that's the thing I do a lot, it's numerical modeling of the climate. We could report that if you take the Mars model, we increase the obliquity as it was 5 million years ago, we will create the same glaciers. That was a fun eureka time. Almost done. I will finish. The future, I will not describe a new mission for the future. What I will describe is the fact that we understand that Mars has been through, have had many different phases. It at high obliquity, some time ago it was very cloudy, it was a glacial era, but maybe at low obliquity, all the atmosphere was frozen and it was a dark sky with a very thin atmosphere. And then in the past we had oceans, maybe rivers, and it changed all the time. So now if you think about it, all we have is a surface with geologists looking at different places. It's a puzzle, an incredible puzzle, 4 billion years puzzled, and we have to understand what happened. So we don't explore only one planet, we explore many, maybe 100 different planets, and we have the records, we have now the present-day planet. And my wish for the future is that we can really improve and solve this puzzle and have a story to tell about the past of Mars. Thank you very much.
Our next speaker is Dr. Minnie Wadhwa, who is director of the School of Earth and Space Exploration at Arizona State University, as well as principal scientist for the Mars Sample Return Program. So, Dr. Wadhwa.
Okay, thanks, Bethany. So, I'm going to start by showing you my favorite childhood photo with my parents. And the reason I show this to you is because I really credit them for helping me to define my path, because really the best thing that they did for me was to allow me to forge my own path. And I really don't take that for granted at all, because I saw that reality for a lot of my friends and a lot of my cousins that I was growing up with, where there were decisions about career, decisions about life, those kinds of things a lot of times were not in their complete control. And I'm just incredibly grateful to my parents for their encouragement and their support, and allowed me to think that I could do anything and be anything. The other thing that I wanted to just point out is that Bethany introduced me as Minnie Wadhwa, and that's my real name. My full name, though, is Meenakshi Wadhwa. And a lot of times people think that Minnie is sort of a butchering of my full name to make it easier for Americans to pronounce. It's not. It's actually comes from a short story that was a favorite of my mother's. This is a short story that was written by Indian Nobel laureate, the first Indian Nobel laureate actually, called the Kabuliwala. And there's a little girl in that story called Minnie. And so there's actually a little sort of a generation of Minnies kind of running around India, actually, because it was a very, very popular story, made into a movie, all kinds of things. And if you think about it, go read that story. It's really pretty cool. So how did my Mars exploration journey start? Well, it kind of started here in grad school. I started working on Mars meteorites as a graduate student. And the picture that you see on the left there, that is a false color image of the first Mars meteorite that I laid eyes on. And you can just imagine, I was trained as a geologist. I had an undergraduate degree from India in geology, and I was familiar with basalts and familiar with what they look like. And here was this rock, looked very familiar, but it came from another planet. It just blew my mind. I was hooked. There was no turning back from that point. And so I studied the trace element geochemistry of Mars meteorites to try to understand something about how they formed on that planet. And that's actually a picture of me in grad school. I'm not going to say exactly when that was, but a while back. And that's the Kamika IMS-3 ion microprobe that I used, the instrument that I used for my work. And maybe I'll sort of date myself a little bit by telling you that when I was in grad school, there were less than a dozen Mars meteorites at that time. And basically, in the last several decades, we've now got something like over 150 Martian meteorites, distinct Martian meteorites. And there's many, many different paired stones, and so there's several hundred, actually, of Mars meteorites that we know about. But you can see that there's actually different kinds of Mars meteorites, but all of them are igneous rocks, except for one, which is a breccia, and it's made up of sort of a jumble of clasts of different origins, mostly igneous clasts, actually, but some could be of impact origin, for example. And you can see some of the incredible textures that you see among some of these Mars meteorites. They're all igneous rocks, as I said, except for the one that's the regolith breccia. And then all except two are younger than about 2.5 billion years. And so we really don't have hardly any material from Mars that dates back to around 4 billion years, when we think Mars actually may have been a lot more Earth-like, perhaps. And so there's a lot, actually, that we've learned from studying Mars meteorites, and I'm actually going to tell you a little, just sort of my top 5, the hit list of top 5 things that we've learned from Mars meteorites. And they're incredible things that we could not know from studying Mars from orbit. These are things that you can only really discern and learn if you bring back samples and study them in laboratories here on Earth. And that's what we have from Mars meteorites. Of course, Mars meteorites have their limitations. They've been weathered by sitting around on Earth. They've been shocked to get us these samples from Mars. You have to sort of eject them with a huge impact. And so they're messed up to some extent. And they're not well understood in terms of their geologic context, and so there's a lot of limitations about them. But what we've learned about Mars, number one, that Mars likely had a paleofield early in its history. We don't know exactly when it turned off, but probably early in its history, maybe around 4 billion years or so, but we don't know that for sure. We also understand that it accreted very, very early in terms of the planet formation processes. Within the first 5 million years or so of solar system history, you had this planet forming already. And it had already sort of, we think it was already differentiated, had a crust and a mantle well within 100 million years of solar system formation. We can understand something about the bulk chemistry of that planet from studying the geochemistry and from modeling of Mars meteorite compositions. We also know from studying hydrogen isotopes in Mars meteorites that, in fact, there's evidence of interaction between the crust and the atmosphere as a result of crustal fluids, water. And so these are the kinds of things that you have to pick apart these rocks to be able to learn that type of information. But we don't know for sure, whether you can apply this locally, perhaps, or if this is the global picture. And so what I'm looking forward to, and you can imagine that, of course, I'm looking forward to the Mars samples coming back, where we can actually analyze these things in labs. And I know there's a lot of the folks here, of course, we have this incredible data set of remote sensing data that we've collected over the decades for Mars. Bringing these back will actually make all that incredible data set even more valuable, because we'll have ground truth. But we'll learn a lot, obviously, about Mars when we study these rocks from a very well-characterized geologic context. But we'll also understand broader questions about solar system formation, planet formation, habitability, all of those types of things that we really are sort of fundamental things that we want to understand about habitable worlds and how they form. So that's my story.
Great, thank you. Our next speaker is Dr. Noora Alsaeed, who is a research scientist at the United Arab Emirates Space Agency. She works on the Emirates Mars mission, as well as the Emirates asteroid mission, which is in work now. So, Dr. Alsaeed.
Hello, everyone. I have a much shorter accomplishment list to pull from, so I am mostly going to talk about how I got to the point I'm at, and then I'll show some of the cool images that we've seen with the Emirates Mars mission. But let's start at the beginning. I'm just really curious, by show of hands, how many of you have heard of Dubai, Abu Dhabi? Okay. How many of you have visited the Middle East? That's a much larger number than I expected. Yay. Okay. All right. So this is probably not the best crowd for this, but I did have this question many times where many people have heard of the UAE, but they've never been able to tell where it is on a map. So it's right there. And that's where I was born and raised. And I spent the first 20 years of my life living in the UAE. And the first time I ever lived abroad was when I came to grad school in 2017. So the reason why I got into grad school and why I even became involved in Mars science was because there was a professor who noticed that I was an extreme nerd and I enjoyed everything to do with space and science and I walked into his office hours asking about quantum entanglement when the course was about astronomy. So he was like, okay, I'm gonna have you work with me on a project. And that project then turned into something that we were able to publish. And that was in the year 2014. And in that same year, the UAE announced the Emirates Mars mission. And that was the mission that launched in 2020. And the announcement was also coincident to when they established the UAE Space Agency. So our UAE Space Agency is really young. It's 2014. That's just a way to highlight how young and new this entire field is in that region, and specifically in the UAE. Hence why I am at a much earlier stage in my career on stage with such amazing, wonderful people, it's honestly a privilege, and I'm happy that I get to represent that. But as you may already have guessed, I was so happy that I get to apply and be involved in science in a level that the entire nation is backing. And so I applied to grad school in Boulder, and I did my PhD there. And I was going to stop it there, but really the main reason why I ended up going into science is because of a list of people that supported me. So here, what I'm showing is a photo of baby me with my brother, who's my #1 supporter. And he wished he was a scientist, but didn't end up going into that. So he kind of brainwashed me into becoming a scientist. And my father, who is, he was actually the first Emirati professor in the UAE in the 70s when they opened the first university there. And so at dinner time, he would ask me to name different parts of the periodic table. So that's the kind of father I grew up with. But it was really loving. It was like a nerdy kind of way of showing love. And then in my bachelor's year, this is the professor that I did that project with, who noticed my nerdiness and really supported me and actually put my name down as a potential student who could go work and do research experiences in space. And then I came to Boulder, and I met these two wonderful human beings who, one of them is in the room, Paul Hain, who I did my PhD chapters with, and Bruce Jakosky, who's an amazing, wonderful, established Mars scientist who was the PI of the MAVEN mission, if you have heard of that. And these are all the people who, in one way or another, really took that curiosity and joy that I have for science and nurtured it and convinced me that I have what it takes to become a planetary scientist, which is what I am right now. So I'm a planetary scientist working mostly on Mars and then a little bit on asteroid science, which is not the purpose of this talk, so I won't go into that. But one of the things that I really, really enjoyed seeing and learning when I first got into this field is looking at the big picture. So, this is a GIF I made showing the transition of how human beings have viewed Mars over the years. And these are all of the global pictures that we've ever taken. Of course, there are many more from the Hubble Space Telescope. And in 2022, we were able to add the Emirates Mars mission onto that list. And you can see the quality getting much better as time progresses. That first one was a sketch done by Huygens, where he was looking through the telescope and then drawing what he saw. And I don't know, maybe the telescope wasn't the best quality, or he's a bad artist. But it's amazing to see how far along we've come with these images. And the thing that I realized when I was putting this together is that up until the Emirates Mars mission, most other missions have been focusing on taking really close-up views of the planet. So they would have snapshots and then make a collage to get a full view of Mars. And until maybe the Indian MOM orbiter, or Mars orbiter mission. That was the first time since 2000-something that we've taken this snapshot of the entire planet's disk instead of making compositions. And the Emirates Mars mission added onto that by taking many snapshots. And you can create these videos that show how the planet is changing with time. And you can see, if you look at the volcanoes over here, can you see the clouds moving and going away as this is looping back and forth? And you can even have, the orbiter stay stationary while the planet spins under it, and you can see these changes. They're way cooler images than just these ones, but these were the ones I could pull up to show the entire disk of the planet. And this was really exciting to me because it's gonna allow us and is allowing us to study daily changes in the weather. And that's not something that we were able to do before this mission was sent. So that's really cool. And this is leading to what I'm really excited about, which is the fact that we have a lot of Mars missions. And we have a lot of data from these missions. So what I'm really looking forward to, I remember, Phil, you said this is, you don't feel, you only cited 7 authors or something for your work. I'm actually really grateful that we have so much data to work with, because this opens up the opportunity to do a lot of synthesis work and take that data from one mission and add it to another mission and then make a project out of that and have these different perspectives. And it enhances international collaborations. I'm so grateful for all of my colleagues that I've met through working in this in the space sector. I've had the pleasure of working with the MRO team, the MAVEN team, the Emirates Mars mission team, and the Emirates mission to the asteroid belt. And then they let me sneak in to the group shot with the engineers. I'm not an engineer, to take this photo with the Emirates Mars mission when it was being manufactured. And then these are some of the wonderful people that I got to be friends with. Here are people that are from all over Europe at a conference that we had on Mars, just everything about Mars. Here are all my wonderful team members from the EPIC team that was the research group that I was part of in grad school. And then I got to go on all of these amazing field trips because they feel bad for those of us who have to spend all that time, typing away. And so they're like, yeah, you can go see the geology every once in a while. So that was fun. And most recently, we got to go to the Yukon and had a Mars Polar Conference there last week where we talked about everything to do with polar science. So that's how niche we're getting with our understanding of Mars. So that's really all I had. I will, since I have a little bit of time, I'm going to show this bonus slide. I don't know if anyone noticed the date that I put on when the UAE was first unified, the birth of the country. This is taken from the Mars 3 lander with the Soviet Mars program. This is the first, I should say, attempted image. The Viking one is the real first image. But it took place on the 2nd of December in 1971, which feels like a really fun coincidence. And, it's national pride. But really what this means is that we have come a long way from being a small desert country to being able to have an orbiter up in space. And I'm so grateful and privileged to have been part of that process and be able to stand here and share that story with you all. So thank you.
Our final speaker is Dr. Jessica Watkins. Jessica is a NASA astronaut, and she is also a planetary geologist who's worked on orbital and rover data of Mars. Dr. Watkins.
All right, thank you so much for having me, and I'm super excited to be here with you all. As you guys know, and as Bethany just mentioned, you're my people, so I'm happy to be back here with you. I'll talk a bit about my journey and then a bit about kind of the last question on what I see the future of Mars exploration to look like, and kind of the steps that we are taking now to ensure that that is going to happen. And I chose this image just as a kind of a lead on to that story, where you can see the how we are using the ISS, the International Space Station, to as kind of a test bed, a learning platform for heading to the moon, and then we'll use the moon as a test bed and learning platform for our future exploration of Mars. So we'll see that connection kind of throughout. So I started my journey as a Mars explorer, similar to Dr. Forget, actually, a naive, clueless engineer. That was it? I started out as a mechanical engineering major in undergrad. That was kind of the thing that I thought that I needed to do. I've wanted to be an astronaut since I was out from a pretty young age, and kind of thought that that was the path to make that happen. So I signed up as an engineer, and quickly found that it just was something, it was just not what I was passionate about, not something that I was particularly good at, and just didn't feel like the right path for me. So I kind of came to a crossroads where I had to decide between following this path that I thought was going to enable me to reach my dreams, or find something that I really loved. And luckily for me, I found both. I actually sat down with our course bulletin. They probably don't even make these anymore, but there's like a giant book with all of the courses available that you could kind of sift through. And I found a few classes with titles like What Makes a Habitable Planet and Planetary Materials. And I was like, whatever this is, that's what I want to do. And I looked up and it was in the geology department. So signed up for my first class and fell in love, was hooked ever since. So I finished that, my degree in geology, focusing mostly on Earth geology and on the terrestrial side, and then went to grad school where I was able to focus on the geology of Mars. My graduate work was looking mostly at landslides on Mars, particularly in the Valles Marineris Canyon. I was working at UCLA with the late Dr. An Yin, and also with Dr. Elman here at Caltech, looking at the emplacement mechanisms of these large landslides. I then went on to do a postdoc, actually here at Caltech, working on the Curiosity Mars rover. And that was just an amazing experience to be able to be a part of that team, start to do some operational work, as well as dig into the details of kind of our in situ data. Fast forward a bit, following that, I was selected to be a NASA astronaut, and then selected to be a part of the Crew 4 mission to the International Space Station. So I went up and spent about 6 months on board the ISS. And at that point, I really kind of thought that most of my time as a Mars explorer had kind of come to an end, and that I was kind of shifting over to a new direction in my career. But I actually found that was not entirely the case. When I got up to station, to ISS, I was struck by the kind of vantage point, the perspective that we were able to have through the cupola window featured here. Most of my work as a graduate student in particular was looking from an orbital perspective. So we're using maps like these in order to view the planet from a perspective like this. So we're able to see, this is the Valles Marineris Canyon on Mars, and we're kind of using our orbital data sets and orbital instruments to get an understanding of the kind of regional picture. But what was really neat on orbit was looking through the cupola window, we were able to get a really similar vantage point. We're about a similar altitude from the surface of the Earth as many of our assets are from the surface of Mars. And so when we looked out and took a photo like this of the Grand Canyon, I was really struck by how similar you were able to see the surface of the Earth in the way that I had looked at the surface of Mars for so long. And the really interesting aspect of that was the knowing that and being able to kind of marry the data sets with what I had seen on the ground at that exact same location. So this is me and my classmates. So we, as astronauts, we get selected as a class. And we were doing part of our kind of basic training is geology training. That is part of what we do. And so this was our class was here at the Grand Canyon doing some of that geology field training. And so it was really neat to be able to see from orbit, from an orbital perspective, a place where I had done field work, had boots on the ground with that in situ perspective, and kind of marry those two. And I was really struck by how similar that is to our exploration of the surface of Mars, how we're able to use our rovers and lander data sets in combination with our orbital sense and our orbital data to really get a full picture of what's going on. And so it was really neat to be able to do that from kind of a personal level, have my field photos look like Google Earth. Was pretty awesome, but just a real kind of full circle moment for me as a Mars explorer. The other aspect of being on the ISS that's really kind of instrumental in this question about what does future exploration look like is that we're able to use the ISS as a test bed, as I mentioned, and really start to look at some of the technologies that we are going to need in order to get to Mars. And of course, it's interesting, Dr. Ullman asked us the question of what does Mars exploration look like in the future? And we have yet to discuss human exploration of Mars, which of course is now kind of the first place that my mind goes. And so when we think about the human exploration side, there are some large challenges to that, one of which is the radiation issue. So, of course, the journey to Mars is a long one, and our astronauts will be exposed to quite a bit of radiation on the journey and while they're there. And so we can do tests on the ISS like this. It's called the AstroRad. It's a radiation vest. And the idea is to try to provide a solution that enables crew members to still work and get things done without having to kind of shelter in place in a particular spot on a vehicle and still be protected from radiation. So we were doing some investigation of that. Another technology demonstration that we were working on while we were on board was growing plants. So this is an experiment called X-Roots, where we were looking at growing plants on board without soil. So soil is an issue for a few reasons in terms of human exploration. One, it has a lot of mass, so it is heavy, which means dollars. It's expensive and difficult to get up to orbit and to other planets. And then it also has a containment issue. So if you were to open up a flower pot of soil on orbit, you would be in a world of hurt. It would be everywhere. And so we were looking at some techniques of growing plants without soil in support of what we might need in future exploration. And then lastly, we were looking at kind of a shift in operations as well. This future of exploration as we go further out into the solar system is going to require us to change how we do things, how we operate. Right now, we have a lot of interaction with the ground team. The ground team is amazing, helping us, do whatever activity or task we need to accomplish. But as we go out further into the solar system, much like we've seen on our Mars rover exploration, we don't always have that benefit of the of timely communication. And so we'll have to learn how to do things more autonomously and remotely. So here I'm actually operating a robot that is on the ground here on Earth, and I'm operating it from orbit. And so that type of operational impact is going to be something we need to figure out as well. And so to kind of answer that final question of what does Mars exploration look like in the future, this is just a kind of a compilation of artist renditions of what working on the surface of Mars might look like. I'm not sure which are true and viable, but what I was really struck by is that each of these images has a human and a robot of some kind, right? A rover or a helicopter, like Dr. Fraeman mentioned. and there is this interaction between the humans and the robots. I frequently get asked the question, so which is it, humans or robots? Which is going to be, more beneficial, more productive for exploration? And my answer is always both, right? We need the robotics to provide a foundation, to do the reconnaissance, to help us understand where is most interesting to go, which questions do we want to answer most, and help provide an understanding of where those locations are on the surface. And then, of course, lay all the foundation for the science that the humans can go and do and get their hands on. And then once we get there, the humans working hand in hand with robots to help enable even more efficient exploration is going to be absolutely paramount. So just thank you for all the work that you all are doing in the community to lay that foundation. And I know that we're talking about it this week, and it's just exciting to be a part of it. Thanks.
All right, thanks everyone. So with that, we have about 30 minutes here for questions. So I will invite the whole panel to come on up, take a seat. Everyone can think about their question here as we get rolling on the Q&A part. So for the reference of people in the audience, there are microphones at each side of the room. I will take the moderator privilege here and maybe kick it off to say, actually every single person here has spent some substantial part of their career working on other planets. Other planets? Like there's just this Mars, right? Why do you spend so much time studying Mars in particular? Like, what is it that's special about this planet? What drew you to Mars, not one of these other lovely 7 planets and moons and asteroids, and why so much time?
Sure, I'll kick it off with one of many reasons, I think. But for me, I'll say 2 reasons. One of the things is Mars has such this tantalizing history. We know that it used to be a very different place, a place that maybe once could have supported life, and it's not today. And to me, trying to answer that question of why and understanding what it is that makes places good for life or not is one of the most profound questions we can ask as humans. I also love Mars because it is a place. We have pictures of its surface. It looks like it could almost be out in the Southwest here, and the thought of being able to visit it one day is so exciting to me.
For me, I'm a geologist, and so it has the diversity of processes, everything from volcanoes to glaciers to rivers to sand dunes, and that the ability to study those processes and to look at that record of history. It preserves what was going on in the solar system 4 billion years ago. And as several people have said, when Mars and Earth were similar, and so that ability to use Mars to look back in time at early Earth and to see those same set of processes, that's what fascinates me.
So I kind of touched on this in my talk, but I fell into it, really, Mars exploration, because I love rocks. I mean, that's that's kind of what, I had been trained as a geologist, and this rock that my advisor showed me, he said, hey, would you like to study this rock that came from Mars? And it, looked so familiar, but it came from another planet. And so that was super exciting. That was sort of the simple reason why I kind of really was excited to study Mars, because it was another planet. And it was we were able to actually study it through rocks. So.
Can I be kind of honest here? If they had done a Venus mission from the UAE, I'd probably be a Venus.
You'd have been all in.
Yeah. I love to
Are you going to stick with Mars?
No, I'd love to study anything. It's just frustrating when you don't have data to work with. So Mars has a lot of data to work with. And so there's less hair pulling when you have a bit more to play around with than, thinking about, well, what is going on Titan? I don't know. So that's why.
I agree with everyone, including you, but it's true that when you study Mars, because one good thing with our status in France, we have a lot of freedom. But I still continue to work a lot on Mars. First, it's a place that you can explore a little bit on the Earth, it's true. As a meteorologist, weather person also, it's true that in the solar system, if you do comparative climatology, it's really close to the Earth. The coincidence is that it rotates the same with the same, the length of the day is 24 hours and 40 minutes. The obliquity is about the same, so the seasons are the same. In the end, you have if you look at the wind, you have west wind at the mid-latitudes, trade winds, monsoon, it's low pressure systems and so on. So it's quite similar. And so these are the serious reason why I think it's a little special. The last reason is the one I already mentioned, is that when we explore Mars, you explore 50 different planets at the same time because of these different phases I mentioned. And this is also a kind of new motivation.
Yeah, I also agree with everyone. I think similar to you, Dr. Forget, I think that comparative planetology, the idea that we can go out into our literal backyard and look at processes, understand processes, how they work on Earth, and then understand in what ways do those processes remain the same and in what ways are they different? What variables can we tweak, or what variables do we have to tweak in order to understand what's changing about those processes on Mars, but having that same fundamental understanding of how things work. I think is just a really neat puzzle, really neat problem to have. And then I'll add that Mars is also one of the best places to answer the question of, are we alone? Is there life out there? It's not the only place, but it definitely is one that's accessible with all the other constraints, thinking about data availability and all of that, that I think really draws me to it as well.
I've heard someone say that it's just a less complicated version of Earth, and that's kind of a nice reason to François give me a look. He's like, no, it's not.
We used to think that. But again, it's a puzzle.
Yeah. Great question up here in the front.
First, thank you all for sharing your really interesting and inspiring stories. I have a question for Minnie, also just a quick comment for Jessica. I just want to say, you've earned that suit, but if I had that suit, I would never take it off. I mean, I'd wear it in the shower. I would wear it to the grocery store. I mean, just... Minnie, my question is, what are the signatures that allow you to determine with certainty that a meteorite originated at Mars?
Great question. So how we figured that out, it's kind of a cool detective story, really. And we would not have figured it out if Viking had not landed there and measured the atmospheric composition. But the first Mars meteorite that we knew for sure, or thought most likely came from Mars, was an Antarctic meteorite called EET 79001. And it was analyzed by folks who looked at trapped gases in that meteorite. And those trapped gases had the exact same composition. If you looked at CO2 or nitrogen, noble gases, exact same composition as the composition measured by Viking. And that was like a fingerprint. And so that's how we know. And we can connect these meteorites by other isotopic signatures. And so, you know, as a group, we think they definitely came from Mars.
Great. Over here, and then yeah.
Sure thing. Hello. Do you see the need for any additional communication satellites, orbiters around Mars anytime soon, with the possible additional missions going to Mars?
Yes. So the way that we operate our rovers on the surface is through the orbiters. We don't send data back from the rovers directly from the rover to Earth. Instead, what we do is we use the small radio on the rover to send it up to the orbiter, and then the big radio on the orbiter to send it to Earth. And so these assets have been invaluable for allowing us to operate the mission and then send back gigabits of data, way more than you would ever be able to send if they weren't there. Right now, we have a fleet of orbiters that have done an amazing job. Some of them are getting a little long in the tooth.
Yeah, that's why I was asking.
So if we have any dream of future surface missions for robots or for humans, we're going to need to set up an infrastructure that's going to be able to continue to support surface operations the way we know.
All right, thank you.
Yes, over here.
Well, hello. First, I want to say it's such a delight to have such an illuminated panel to be listening to. It far eclipses some strange electoral contest that's being undertaken in some dusty corner of another planet besides Mars. But I had 2 questions regarding the transition of life from Earth to Mars, a primary question and a secondary question. The primary one is, I believe it is most directed to Dr. Watkins, but to everyone as well. What kind of research is being done on the transmission and health of pollinators and nematodes and bacterium that are, and mycelium even, which are essential for healthy ecosystems on Earth in order to provide, food and other substances for future astronauts on Mars? That's the primary question. And the secondary question is, has there been any calculations on the possibility of contamination of ancient relics of Martian life by microorganisms from Earth, especially given the troubling circumstances of the longevity of tardigrades in space? So there's a primary and a secondary question.
Yeah, so I can start with the first part and tell you that there has been experiments on board the International Space Station, both on nematodes as well as tardigrades. We have brought them up on a supply vehicle and done work on. I can't tell you exactly the details of the experiment because it was after my mission, but we are looking at the sustainability and the how they're able to live and grow in the microgravity environment. So those questions are definitely being asked, and using the ISS as a test bed to help answer them.
And we're growing plants too, and their root structures, they're doing okay, right? Even without some of the soil microbes.
Yes. The plants that we grew did really well. We grew actually several kind of cherry tomatoes. They were gorgeous, but I'm still really bitter. They didn't let us eat them. And then the next crew came up and they got to eat them.
What? Not fair. Anyone want to take the other question about are we contaminating Mars?
Yeah, so that's a concern for sure, because we want to make sure that the samples that we are collecting and bringing back or planning to bring back, we're not actually contaminating them with Earth life, because that's what we want to try to look at them to see if there's potentially ancient life, evidence of ancient life. So there's two things that we have to do for that. We have to control the contamination that we might bring from Earth to Mars, and we have to have the knowledge of the things that we can only get it down to a certain level. We can do the best that we can, but human beings are, and when you try to put spacecraft together, some things you cannot avoid.
Like shed bacteria.
Exactly.
In cells.
Yeah, exactly. And so contamination control, contamination knowledge, those are both really important things. And when Perseverance, the rover that's there now collecting the samples, those tubes that the rover has with it, that the samples are collected in, those were probably the cleanest things that have been sent to space. Before they were launched, I think they were really, really very, very cleaned very carefully. And when we bring those samples back as well, they'll be treated very, very carefully to make sure that we don't contaminate them. And then we're using things like witness plates and witness blanks, and some of the tubes actually are recording the contamination that the rover sees. So there's different things that we're doing to try to mitigate exactly those kinds of concerns.
And for the ancient life question, it's not so dissimilar. We know that there's ancient life on Earth, including ancient bacterial life, because we see the record in the rocks. And, it hasn't all been eaten by modern life. So there's some natural things working in our favor, too. It's a great question. Yeah. Yes?
Hello, I have a question since a lot of the funding and data and stuff like that for Mars comes from national sources. And so like in the long term are very subject to the whims of politicians and national leaders and stuff like that. How do you guys balance your long-term scientific goals over the course of decades, it seems, with the whims of politics? Because, you know, at any moment you can see like a funding cut, or maybe someone wants to pivot. How do you guys sort of deal with that, especially for Mars?
Yeah, there's both a policy question there and a personal question too, I think. We could take, so panelists can take it in any direction. It's a great question.
I'll start. So you raise an incredibly important question, because the scientific community tries to stay organized and focused so that we're not at the whim of the changing political climate. And so for 30 years now, NASA's had a process where once a decade, a group of 100 people get together, and they spend 2 years, and that most of their lives trying to sort out exactly that question. I had the great pleasure of leading this group, or co-leading this group of cats over a couple of years. And it was, but it was a really important process, and I believe, I've drunk the Kool-Aid, that effort provides the science community with the stability to be able to say, these are the things we need to do and overcome the political whim of changing policy. So I think that's worked really well. I hope it continues to work well going forward.
Go ahead.
That.
Yeah, I made Michael and some of his classmates read the Planetary Decadal survey as the introductory text in Intro to Planetary Science. So, you know, now you get to ask the questions.
I just wanted to add that you can do a lot of Mars science without having a mission on Mars too. And so there's two reasons for that. I mean, there's a lot of modeling work that's happening right now. And of course, it's being informed by the data, but we have enough data that we can at least, you know, if there is a lull or a break in funding for whatever reason, and there's no new missions for a few years, there's enough to continue the research. And there's also a lot of science that you can do with planetary analogs, and there's also so much data that there are things that people haven't yet discovered in data that's already been taken. So it's not too attached to the whims and changes because of that structure, because of the structure that Phil mentioned, and the fact that you can do a lot of science without having missions there. So, yeah.
I can address one aspect of your question, which was how do you deal with that personally? And it's the same. It was funny to explain how we can work on missions that fail, that crash. It's also true at the programmatic and even political level. So in practice, most of us work on different projects, except some engineers, for them it's quite difficult. Sometimes they spend 10 years on one project and it crashes, or it is cancelled by something. So there are many examples. I told you about actual crashes and technical failures, but you have also political problems. For instance, we've been working for years on a project named ExoMars, and it used to be a joint project with NASA. One day, Congress decided the NASA contribution was cancelled. It was a disaster and so on. We joined with Russia, and then it was supposed to be launched in September 2022. And we don't work with Russia anymore. We don't like them. So fortunately, NASA said, we can join. And now we are afraid of NASA saying, oh no, Congress has changed. We don't. So it's life. So the answer, personally, is true for crashes and political problems, is that for most of us, we work on several projects for years, and when we have a crash, a cancellation, okay, we have other projects.
Like you have a world-leading institute for climate modeling of Mars and other planets, for example. That's just, you know, a side gig against all these missions, for example. Yeah. Yeah.
Hi, my name is Pablo. I'm an intern at JPL. My question goes to both Dr. Franz and Dr. Watkins. As someone who's very passionate about exploration and being out there in the field and working, but also loves science and engineering, most of those career paths tend to come when you're an astronaut and not as much as when you're like an engineer and stuff. How have you guys been able to combine that in your careers as you get to that journey?
You mean getting out there and exploring, like
Yes,
on
ma'am.
parts of Earth? Yeah. Okay. Exploration of Earth. How do we get to do that and mix it in?
Yeah, definitely. So I think, even by asking that question, you're on the right path, right? I think being really intentional about it is the first step. It's not as you said, it may not be something that will kind of fall into your lap, but really seeking out those opportunities. There's, even just NASA alone puts on so many different programs, field trips that are associated with the conference, or that are available for students. Internships is a really big piece of that as well. Certainly in my career, I've done several NASA internships that have really allowed me to kind of apply my kind of academic endeavors in more of a explorative way. And that has really opened doors for me that have allowed me to have more of those kind of opportunities and experiences. So I think seeking them out, seeking out people as well, mentors that can help you find those types of opportunities will go a really long way.
Thank you for this question. As I mentioned, I have to say that the science what we all do with our computers, maybe some lab work, is already an exploration, so that fulfill a large part of my dream of being Jacques Cousteau, if you want. But nevertheless, even if you want to be a super serious scientist, okay, you're tempted to sometimes do some field trips. So for instance, as for me, I've been lucky to have excellent scientific reason to set up and have a program in Antarctica, and I go there, and it's a nice adventure. We have different, station that we can work in, and there are, in fact, Antarctica is like another planet, so we have to learn all these extreme things, very exotic and so on. We learn about Mars or that, so on, so on. So we can do that, but I want to really emphasize the fact that in practice, scientific research, including planetary exploration, of course, is a really exciting exploration, and it's already a lot for a former teenager who was dreaming of going everywhere.
Thank you very much.
Yes.
Oh, hello, my name is Christopher Reinhardt. I'm a high school student at Dane Regional STEM School in Ohio. And I was just wondering, if you were to give any advice to someone who would like to be a future Mars explorer, what would it be?
Excellent question, and I'm so glad you're here. My advice would be follow your passions about what you like doing best and think about how that connects to space exploration. Mars explorers can be scientists like us, can be engineers like some of us used to be, and I'm sure some of us are in the audience, mechanical engineers, aerospace engineers, electrical engineers. We also need communicators, people who are able to tell the stories about what we do in space. And so finding what it is that you love to do and that connection to space exploration, I think is going to be the path that's going to help you get as far as you want to go.
I think I'm close enough to high school that I remember exactly what I did. I honestly signed up for so many things. Every time there was an event that had to do with space, or it was mostly like physics or galaxies, whatever it was, I signed up. When they asked for students to send to the US for doing a research experience, I signed up. I tried to put myself out there because it is partially luck, but the more chances you take, the more opportunities you take, then the higher the chance that one of those will luck out, and then you'll end up in a position to be a Mars scientist. So keep putting yourself out there, like you're doing now, which is great.
I could add, I always also, when we are asked a lot this question, because of course it's and so of course often I reply that. I say, yeah, follow your passion, where you're good, and so on. But sometimes I also add, just in case, just work math, physics, strongly, be good, and then everything will be easy.
Great, thank you.
Thank you.
All right, we've got a little bit of time left, so we're going to try to do some lightning or some shorter answers. So I'm going to go here, and then here.
Hello again. With the renewed push to the moon with Artemis, where do you see Mars exploration, interfacing with Artemis and moon science?
Yeah, I guess that's me. Yes, so we're super excited. Thank you for the question and for bringing up Artemis. You're doing my job for me. But yeah, we're super excited about the Artemis program. And as I mentioned, we do see Artemis as a stepping stone towards Mars. The kind of the overarching program at the NASA headquarters level is called the Moon to Mars program, and that's what Artemis is housed under. And so it really is seen as the connecting point that's going to allow us to get to Mars. And so we're really looking forward to using just kind of learning how to operate away from home. So as I kind of mentioned in my talk, the notion of dealing with a time delay. How do we train astronauts to do science without having a scientist in their ear, which is really kind of how we do science on the ISS. What does that look like? How much training do we need? And the answer to that is always more geology training. Don't worry. And then of course there's the technical aspects of that as well. Understanding what technology do we need in order to to move on and off of the surface and to attack the radiation problem and the propellant issues. So the questions that we are hoping to answer, the challenges that we're hoping to overcome in the process of getting to the moon will really serve us in our exploration of Mars as well. From a scientific perspective, of course, the questions that we can answer on the lunar surface also help our understanding of Mars and place everything into context with the formation history of the Earth and the solar system and the moon and Mars's place in that whole picture.
Great, thank you.
So
yes.
My question goes to Jessica. So as a geologist, background astronaut, what if you only have like 1 week to train a non-geological background astronaut to explore, say, Valles Marineris? You only have 1 week geology course. What do you think is the most important material they should study?
All right,
goodness.
The crash course from Professor Watkins.
1 week. I think I probably wouldn't send them, quite honestly. That's not enough.
Qualified?
Right, yeah. It's an interesting question. We have had the pleasure of getting to spend a little bit of time with some of the Apollo astronauts who received really in-depth geology training, like almost to the equivalent of a master's degree before they went to the surface of the moon. But you ask some of them, what do they remember about their geology training, or what did they kind of take away? And the disclaimer is that they're being facetious here, but one of them will never forget said, all we need to do was just pick one of every color. That's
good advice.
I mean,
that is good advice.
This is the problem, is that now all of my classmates think that that's what geology is, and they're not all that. They're not no. So it would maybe be something along those lines. It's really, I would say, identifying both what is normal for this area, so being able to explain or pick the right sample that is indicative of the area, and then anything that is abnormal is also equally as important. So anything that stands out because it's a different color, because it's a different texture, anything about it that looks different or interesting is probably going to be interesting to the scientific community as well.
Excellent. Yes.
Hello. BJ from UAE University. So my question to Jessica, maybe a different kind of question. So what do you feel about future of a manned Mars mission without the International Space Station in place, and until we have the lunar gateway in future?
Sorry, so the question's about manned Mars missions before we have a lunar gateway?
and without the International Space Station?
Because the ISS is going out of commission. I think that was like in the news, and
Yes.
people wanted to know what's in between.
Yeah, absolutely. So in terms of kind of the timeline, I can talk to how we see that going forward. So you're right that the ISS is currently planned through 2030, and then will be decommissioned and handed over to the private industry side of things. They'll kind of take over the low Earth orbit operations, and when we make that transition, then NASA will then be able to focus on going out further into the solar system, namely to the Moon and Mars. By that time, it's not entirely clear to me whether we will have a gateway established in orbit yet, but we'll certainly be pushing towards going directly to the surface, even without having gateway in place yet. So we will be kind of putting all of our resources and energy towards that lunar surface, and then building up kind of a colony on the Moon as well. So we're working on that architecture on the surface to then be able to go kind of back and forth between a gateway and a surface operation as well. And then from there, I think the intent is to spend some time on the Moon, learn those lessons that we were kind of talking about, overcome some of those challenges, and then be able to build on that to go out to Mars.
Great, thanks.
All right, I'm going to take the moderator's prerogative here and do the very last question, which is I'm going to ask you to just say, what is the mission that you're most excited about for the future? It can be anything at all, even if it's something that doesn't even exist on anything except a drawn-out napkin sketch of a mission. What mission are you most excited about for the future? Short answers. This is the lightning round. Final question.
All right. Continued operation of our rovers on the surface and helicopters to Valles Marineris.
A really deep core into one of the ice caps of Mars.
So this doesn't have to be a real mission, right?
It can be whatever you want it to be.
I would want one that's like a mission that collects samples from every one of the planets in our solar system.
Sample return not just from Mars, but from everywhere.
Every
I love
planet
it.
in our
I love
solar
it.
system.
For me, it would be really cool to have a Venus mission, honestly. That's the last one, the unexplored frontier. But that would be really cool.
A Venus rover, you mean?
No, not a rover. No. Maybe your balloons. Your balloons, we could send them to Venus. Can we?
There were some already in the past. If you think, honestly, I don't think there is a coolest thing to do than drilling deep into a deep aquifer to check if you have Martian bugs living there.
And it's boots on the ground for me.
Let's get him there. All right. Well, on that note, I want to first of all thank the technical staff who's had an awesomely long day. Thank you for helping make this happen. And then thank you to our panel for sharing your thoughts, and to all of you for your great questions. We'll be up here for a few minutes, then head out of the house because I know they want to close it down. So thank you, everyone, for coming. Appreciate it.